hello, hello. কিছু বলার আছে? করে মানে হাওয়াটা বেরিয়ে যাচ্ছে না। ও আচ্ছা, ঠিক আছে। Okay, so am I audible? Please respond. So are you trying to say something? It seems you're okay. You're muted now. Fine. Okay. So good evening, everyone. Welcome to this NPTEL PMRF session on real-time digital signal processing. I am Shouharda Ghosh, a first-year PhD scholar in the Department of Electrical Engineering at IIT Gandhinagar. I have completed my dual degree BTech plus MTech from IIT Kharagpur in the field of microelectronics and VLSI design in electronics and electrical communication engineering. Um, this is week 7 and we have covered a lot of material as of now. Today's session I shall be talking about adaptive systems and signal processing, which is basically the content of week 7 as well as week 8. So we have a threefold objective in today's lecture. We shall first provide the motivation behind adaptive signal processing, why we are going towards this adaptive, why aren't we just happy with the earlier DSP stuff that we have learned in the previous weeks. Then we shall briefly brush up our fundamentals of basic probability theory as well as expectation and other operators, which we will find useful in adaptive signal processing. And lastly, we will conclude with a good discussion on LMS, or the least mean square algorithm. Least means square or least mean square. Okay, so just confirm if my screen is visible or not. You can write in the chat box as well. Okay, so it's visible. I mean, it would be better if you can switch on your mics and then respond if that's working, because these sessions are recorded sessions. So if you respond through the audio channel, then in that case it will be recorded and it will be useful for the other viewers in the YouTube recording sessions, those who have not been able to attend the session live. Okay, so let's start with the motivation. Okay, so first we'll talk about motivation. So in a typical DSP session, in a typical DSP problem, what we do, we have some kind of a signal. Let's say, for the sake of simplicity, I am assuming it's a sinusoid of fixed frequency. X of t equals to a sine omega naught t. Okay, so this is the kind of signal that I want to hear, but then the signal is unfortunately mixed with noise. So this, as we know very well, is, we are assuming that this is an additive white Gaussian noise. Okay, and the properties of AW region had been briefly discussed in the previous session, so you can watch that as well. So we get the signal, it says ZT, and then what is our main objective? Our main objective is that this ZT is actually available to us in a digitized format that we call Zn. Okay, so for sake of convenience, we replace the noise by W of t, and we write here this is our signal. So since we are writing the time index as n, there is an implicit sampling rate fs, or an equivalent period sampling period ts associated. So what is z of n? Z of n can also be written as z of nts, which means at time instance which are integral multiples of your sampling period, it is x of nts plus w of nts. Equivalently, you can also have the digital equivalents, which are the signal being sampled at Ts and the noise being sampled at Ts rate. So x of n plus w of n. Okay, now what happens, we know that this signal x of n, let me try to highlight that with a yellow color. Okay, so this signal is highlighting with a yellow color, and this let me highlight with some light green, the noise I highlight with a light green color. Okay, so what happens in the frequency spectrum is that we very well know that the xn, which is a sinusoid of a fixed frequency minus omega naught, is the yellow line visible? Please confirm. I guess I should choose a different color maybe, because yellow with mean white isn't good, so maybe I can choose orange. Okay, so we very well know that the sinusoid spectrum are just two simple sines, two simple delta functions placed at minus omega naught and omega naught. I should rather write this as omega naught. So why how is this small omega naught related with the capital omega naught? So this omega naught we very well know is omega naught times Ts. This is radian per second, and this is second, so our equation is also dimensionally consistent. Wait, let me check if the mic is being recorded. Yeah, the mic is also being recorded. Oops. Okay, good. So you see I have this minus omega naught and omega naught over here, which is the signal, but then this is the corresponding to the xn component, but then I also have the noise. So we very well know that this frequency spectrum of this HWGN is flat all over from minus pi to pi. So let me shade this up so that you get a good feel of the same. This is our spectrum of the received signal z of omega, and this is nothing but x of omega plus w of omega. Now our objective is to eliminate noise and extract the sinusoid. Rather than sinusoid, we actually cosine tone. So a single frequency is termed as a monotone, a single tone signal. Okay, so very simple. Can anyone of you tell me how do we do this in the digital domain? In digital domain, Shabrish and Jagannath, can anyone among you tell me how do I extract this minus omega naught?
Fourier transform.
Fourier transform is a tool which helps me convert the time domain to frequency domain. So it's not something like kind of it helps you to analyze things in a better manner, but then I want them to remove, whether it be time domain or in frequency domain. You are correct that I have to do it in I will be doing it in frequency domain. What should I do so that I get these and remove this stuff over here? Any guesses?
Band passes.
Absolutely good. Oops. So yeah, so we shall be using a band pass filter. In fact, it's a very narrow band filter because I have to extract only almost minus omega, a very thin pitch. So how do I denote that? I have a minus omega naught minus omega naught, and then let me blue color. Okay, so the response of my band pass filter will be something like this. It's a narrow band, very highly selective filter which is only chooses the frequency omega naught and eliminates the rest of them. So from minus pi to pi we have our noise. So after I filter it, post filtering, what I get is minus omega naught, small band of noise. It's just negligible compared to what we had previously. Our entire band was filled with noise that time. So we have this narrow, almost a very short band of noise, and our entire signal we have got it back. Okay, so this band pass filter, let's say h of omega, let's suppose I assume that its impulse response is an IIR filter, sorry, FIR filter. I can do it IR also, but for some reason I am taking it as an FIR filter. You can easily go to MATLAB and then design the you can put in the specifications such as the pass band, stop band, ripples and all that stuff. I equal to 0 to L minus 1 L tap filter, H of I del of n minus I. Okay, and equivalently you will have a kind of filter structure x of n. So you have the delay elements and that I taught in the previous classes. You have the coefficients h of 0, h of 1, h of 2 all the way till h of L minus 1, and then you add them up, similar to what we did in our previous lectures. Okay, so a very important point to note over here is that my omega naught is known to me, so there is only one filter which can one band pass filter corresponding to this minus omega naught. So because I know them, all these hi values corresponding to FL is fixed. Okay, so automatically the multipliers over here h0, h1, h2, hl minus 1, all of them are fixed, right? Now let's suppose for some reason, I mean this signal can be anything that I'm talking about. Okay, it can be a signal from a enemy ship, an enemy submarine. Okay, and the omega naught, this omega naught that you can see over here can be some kind of a signature of your enemy. Okay, and my submarines, I have my submarines deployed throughout the network underwater, and if anybody detects this signal, okay, so I realize that my enemy is near around. Okay, now let's suppose the enemy does a trick. Rather than omega naught, it changes its frequency to minus omega naught hat plus omega naught hat. Okay, earlier it was somewhere over here. Let's suppose omega naught, omega naught. Okay, now I have this one over here. Okay, so correspondingly in the digital domain, what will happen? I had the same h of omega which was designed for minus omega naught and omega naught, but then my enemy played a trick with me. He has its frequencies change to minus omega naught prime and omega naught prime, where omega naught prime is omega naught prime times Ts. Okay, so the sampling period is system dependent, so it's constant. So what's the result? All I get is just the band of, and there's noise, obviously I mentioned earlier there's this noise, so I'll just get a bit of noise around omega naught, and I feel that my enemy is not here, so I slowly move into that area and he shells me out and I'm dead. Okay, so you realize what happened, that because I fixed my frequency response of the filter, I made this filter independent of the characteristic of the signal. So if my signal characteristic change, some kind of a statistical characteristic or some kind of intrinsic characteristic, if that changes, then I have no clue what is going on with me. Somebody can kill me, somebody can, you may even lose a signal, you may your plane may crash into some other plane, your plane may not land into a certain area, your rockets may fail as well. Okay, anything can happen. So here comes the idea of adaptive signal processing. So what does it do is that it tries to manipulate your filter such that it changes with change in input signal characteristic. So basically this field of adaptive signal processing has basically two parts involved. One is the filter design and second one is an adaptive algorithm. So what does the adaptive algorithm actually talk about? It talks about how should your filter change. I mean, what are the rules? How should I manipulate the omega naught of your band pass filter? How should I change the notch? Okay, so what happens over here is that in our practical examples, this example that I told over here, the solution to this problem, when if my enemy changes his frequency, I have something called an adaptive line enhancer. So what it does, if it changes to minus omega naught prime, then correspondingly your filter will also change its center frequency to omega naught prime. And why it's called line? Because it extracts sinusoids, and sinusoids have the frequency spectrum in the form of lines. It's called line. It looks like a line. It's called line spectrum. In fact, when you had studied about, yeah, you have raised a hand. Yeah, Aviral, you have any doubt?
So what is that omega naught frequency?
Okay.
Like omega naught is
So I guess you were not there in the beginning. So basically what I was telling is that, let's suppose I have some kind of a signal that I want to detect. Okay, and this signal is actually corrupted by noise. So we have the equivalent signal zt, which is the summation of signal and noise, and we get a digitized version of this zn, and the underlying sampling frequency is fs, or the sampling period is ts. So this x of t, for simplicity I am assuming it's a sinusoid of frequency omega naught, and then the zn you can equivalently convert into summation of xn and wn. So wn, as I had mentioned, is additive white Gaussian noise. So additive white Gaussian noise has a power spectrum which is flat throughout the minus pi to pi range, and x of n is a sinusoid, so it's equivalently you can represent it as sines delta functions. Okay, So our objective was to eliminate this noise, okay, and just get these signals in case they are there. So we had developed a band pass filter, very narrow band pass filter, which extracts signals only at omega naught and eliminates the rest of them. So you can see over here I got that omega naught thing. And since we are fixing this omega naught, the coefficients of the filter are also fixed. So in an equivalent implementation, the multiplier coefficients h0, h1 all the way to in h of l minus 1 are fixed. It's fixed in your hardware. You are done with it. But then let's suppose that my LME does some kind of a trick. This is a hypothetical example. Something else may also happen. So my enemy changes its center frequency to minus omega naught and plus omega. Changes frequency to omega naught prime. I should have given the prime symbol over here. Yeah, so omega naught prime. Okay, and in the digital domain, now if you use the same bandpass filter, what you get is nothing, because the signal is actually at minus omega naught prime, and I am tricked that that there is no component at omega naught, so my submarine is not here. So I enter into that zone, and but since they are there now, they have changed their frequency. I get into the zone. They know that I am here, and they shell me out. And that's why we said that we require some kind of.
But if your center, if that omega naught is not shifted to like omega naught dash,
Hmm.
right?
Hmm.
So you're saying that they like since like this value is, you're saying 0, right? Because the band pass filter is now at omega naught, because the band pass filter has a center frequency at omega naught.
Hmm. Hmm.
So
Hmm.
you're saying that they'll be able to find my location, but how is that possible?
I'm saying that let's suppose, I'm just giving a hypothetical example where I enter into a zone. I enter into the they are locate. I'm trying to locate where they are. Okay.
Okay.
I'm assuming that I'm emitting a constant frequency. I'm not saying that I'm also playing the trick with them. In that case, things become more complicated. So there is that's an entire different domain of defense electronics. Okay, so just for example, I'm also a kind of a simple guy. So I just go in over there. I'm emitting constant frequency. So I also think that they are also simple like me. So they are also emitting the same frequency. So I enter into a zone. I see that okay, there is no at omega naught there is no sinusoid. So okay, let me enter, let me go a bit forward, and then the moment I go forward, but then actually since they have changed their frequency, I am tricked into realizing that they are not there, and but they are actually there, and then they
Okay.
hit me. Got it right?
Okay, I got it right now.
Good. So that's where adaptive signal processing comes into picture, where based on the signal statistics or based on the parameters of the signal, we have to change our filter. Okay, so that is a big challenge and a big interesting field, and personally speaking, I am working in this field and it's really exciting. And in fact, this adaptive filter signal processing is, you can consider it as the fundamentals or the basic roots from which the modern deep learning machine learning algorithms have grown up, although they have it has diverged into a different direction, but then you can trace back its roots to adaptive signal processing in one way or the other. And we shall learn a very basic deep algorithm which you can connect with deep learning as well. So adaptive line enhancer that I mentioned, so what it does is that based on the how on the frequency change, the filter parameters also change. So we shall not be discussing much about the detailed implementation of this. This was just an example for explaining the giving the motivation. Okay, so basically the general structure of an adaptive system looks like this. So you have some kind of a input signal, okay, and then you have some kind of a, okay, let me name them first, let me write them first, and then I'll, okay, so here's my input signal xn, and I have some kind of a reference signal dn over here. I mean, in this adaptive signal processing, in most of the cases we have to consider that we have a reference signal from which we want to compare with to get some kind of a good metric. In fact, if you have done machine learning, or if you will be doing machine learning, this is very similar to something called supervised learning, where if you are learning about, if you are training your machine to identify whether an image is a cat or a dog, then before you when you start training that, you provide it labeled images. You show it hundreds and thousands of images of cats and dogs with the labels given as cat and dog. Okay, so that's the supervised learning regime, and this one is also belonging to the supervised learning regime. Now here you are training it to the desired signal dn minus plus. Okay, so this dn over here, so you get an error signal en over here, and then you have the adaptive algorithm over here. This xn and en are input to the adaptive algorithm, and then this algorithm tunes the filter coefficients. Okay, so you have, as I mentioned earlier, there were two parts: the filter design and the adaptive algorithm. So this is the filter that I was talking about. Okay, and this is the algorithm. So the core, this is the heart of ASP. So the way you build this algorithm will determine whether your company makes a profit or a loss. In fact, if you look at Apple MacBooks features, so one of its features is something like kind of a beam forming speakers. So it kind of tracks where you are, where the voice is coming from, and based on that it tries to okay, so I shall not be using that as an example. I would rather, yeah, so okay, let me use that as an example. So basically, when I told you that here the filters are changing, in the case of the beamforming speakers, what they do is that they electronically steer the microphones. Okay, so if you have learnt about beam arrays, antenna arrays in electromagnetics, then you must have learnt about the array factor, and then how you change the phase shift between each of these array elements, and then based on the phase shift you can steer the antenna look angle anywhere you want by changing the phase difference of the signals received, or the steering of the antenna. Similarly, the microphones you have, you can also change their phase shifts, and accordingly you do it adaptively. So my voice is, I am speaking some way, so based on an initial estimate of how the amount of strength that each of the microphones are receiving, they will change their strength phase shifts. For example, I am speaking from here, is okay, and there's a mic over here, there's a microphone over here, there's a microphone over here, so all of them have some kind of a variable delay delta 3. So you sum them up, and then you also have some kind of a reference microphone, and based on that you try to change these. So maybe initially delta 1, delta 2, delta 3 are values are such that their response, their phase response will be picking up maximum volume from the upward direction. But based on the kind of signal that this is getting, and the reference signal, so some kind of an adaptive algorithm will work over here, and based on that they will tune the delays over here, and based on the tuning, my microphone will start picking voice in this direction. Okay, is this clear? Any confusion? And this is called beamforming, adaptive beamforming. This is a highly specialized area of adaptive signal processing and is gaining a lot of importance, be it in defense or in civilian applications, even applications such as your Amazon, Alexa, Siri. You have these audio devices placed in one corner of a room, so the moment you speak, it gathers an information about a location and it tracks upon you, and after it catches hold of you by a beamforming, it can focus all its energy into you. Yeah, Aviral.
Like you said that the delays for each microphone are different, right?
Mm-hmm.
That is okay because of part difference. But so the what is the adaptive algorithm doing actually? So is it like tuning all the delays to the reference?
No. So what is happening is that, as I mentioned earlier, that you need some kind of a reference to understand whether your signal is correct or not. Okay. So what is happening actually? Delta 1, delta 2, delta 3, all of them are getting tuned with respect to the reference in some manner. Okay, I am not going to tell you how it is going to change because it has a lot of math involved. Okay, and I have to study that separately once again before trying to teach this over here. So using some kind of an algorithm, I denote that by f, and some kind of an error metric. Okay, so the error metric or the kind of there's some kind of an objective that you have to maximize, and the objective in this case would be to maximize the volume it is getting from me. Okay, maximize the signal to noise ratio that it is getting from me, and based on that it tries to steer the delta t1, delta t2, delta t3. So, it's some kind of an optimization problem, you can say, where you are trying to maximize the cost function. The cost function in this case can be the signal to noise ratio uh, of my voice with respect to the parameters delta t1, delta t2, and delta t3.
Okay.
Okay.
Ah.
So is this clear now?
Okay.
Clear. Okay, good. So that's a basic about the adaptive algorithm, and in most of the cases, majority of the research is performed on FIR filters. The reason being, they are always stable, and although we have research on IIR filters, but we need to be careful with them. And why do you need to be careful? Because they have to have their poles in the unity circle, and in case let's suppose my pole was here initially in iteration 1, in iteration 2 I come over here, in iteration 3 I get out of the circle, so that means my system becomes inherently unstable. So that's the reason why most of the people or most of the systems engineer don't prefer going for IIR filters, although there are techniques or there are works going on in IIR filters, but most of the implementations, most of the work is only on FIR filter because they are easier to implement. They have and first of all, they are stable, they are always stable whatever you do with them, and ease of implementation is also there. You don't have to worry about other quantization effects that you get to see in the IIR filters. Okay, so we are done with our first objective, and the second one I shall do it a bit briefly. Probability revision. Okay, so this might be boring for some of you, but I am doing this for the sake of completeness, because people who might be watching this session later on YouTube may find it useful. So when you learn about probability, so there is an inherent probability density function involved in it, or what we call as PDF. And when you have a PDF, let's say I take a location x and a small interval x plus dx. So what is the probability that this x, capital X, I call it a random variable. Okay, the probability that the random variable lies between x and x plus dx is given by this quantity and this. What is interesting and important to note over here is that this width exactly dx so the probability that the random variable lies between in this zone is dependent on two things. One is the width of the interval and some kind of a function of the position of the interval, and the function that determines the position at which position you are more likely to get a value, less likely to get a value. That function is called the PDF, or the probability density function. And as expected, probability is always greater than 0 and it's a real number. Then you have this property that probability that it lies between two numbers is the integral of this thing. Please bear with me because some of you might be finding this boring. Then probability that x lies between minus infinity and infinity. In that case, if anybody feels that I'm going a bit fast, you may also mention that. I have no issues. So the probability that x can take any value is always 1. You have to have some value. Okay, so it's a certain event. Then you also have the average value of random variable, and that is we denote by expectation over x, some kind of a function of the random variable. How do we do that? It's a weighted average, where your weight is this PDF by dx by integration of minus infinity px of x dx. So this actually looks actually a weighted average, so we divide this by px dx, but since this integral is well known as 1, we obtain the p expected value as px of x fx dx. Someone's mic is on. Okay, thank you. So this is the expectation average value. So in case our fx of x is the random variable self, we call this the mean. X fx dx, or we denote mu x. mean, and then we may have the function, the squared value. You have the mean, how much far is it around. Okay, so expectation of x minus mu whole square integration x minus mu whole square fx dx. This is called sigma square or the variance. A low variance means that your random variable is less likely to be far away from the mean, and higher value varies. It means you have a good probability of the random variable to be far away from the mean. So it can also be calculated as expectation x square minus mu square. Okay. Similar things hold for two-dimensional random variables as well, like two-dimensional Px comma y. So where do we use it? So it's called joint PDF. Okay, so in earlier case when we had one variable, we talked about a strip of line. Now I shall show a patch of area where x can lie in this region. Okay. So it's like, what is the likelihood that x lies in this patch? So that's the location, I mean where am I centered around, that's given by the joint PDF, as well as the area of the patch. This dx and this dy, dx dy. So accordingly you have the equivalent probability formulae y1 y2 x1 x2 y1 y2 px comma y dy dx. Then you have probability that they lie in the entire space, and which is a certain event is px comma y, again repeating the old stuff, it's 1, and then expectation of some function of the two random variables is, at the end of the day, this function times the probability in joint PDF. Okay, this is the average. And then in this case, let me talk about a special function f of x comma y as x minus mu x and y minus mu y, where mu x is actually mean of x and mu y is mean of y. Now when you take expectation of x minus mu x and y minus mu y, which you can equivalently write as x minus mu x, y minus mu y, px comma y, x comma y, dy dx. This quantity is called covariance, c x comma y. So covariance says how closely the random variables x and y are correlated. In our previous session we had talked about correlation between signals, and I had briefly mentioned about the random variables part as well. So it's like c of x comma y much greater than 0, meaning x and y are positively correlated. So the example that time I gave was the number of hours in spent in numericals, that was our x, and the gate exam score was our y. Similarly, when this covariance is a very negative number, so we say that x and y are negatively correlated, and the example that we gave was the price of tomatoes and the market sales, that was corresponding to the, yeah, that's true in economics, that whenever the price goes high, the demand falls down. So, and this was our negatively correlated random variables. And then we have talked about this, where they are and y are uncorrelated, which means that whether x decreases or y increases, whatever happens, they don't affect each other. So the example was the size of shoe and GPA in 5th semester, that was our y. So the size of your shoe should does not affect your GPA in any semester in any way. So they are uncorrelated random variables. Okay, so one thing to note over here is that covariance, there's often a confusion. Covariance C of x comma y is expectation x minus mu x into y minus mu y, and the term correlation, okay, these are two separate terms, r x comma y, which means expectation of x into y. Okay, an important point to note over here is that when covariance is 0, it implies x and y are uncorrelated. And when x and y are uncorrelated, what does it mean? It actually means that your correlation is equal to mu x into mu y. I hope this is a homework for you to solve. Based on this definition, C of x comma y equal to 0, you can solve for yourself and check that that the correlation is the product of the means. But correlation equal to 0, which means that r of x comma y equal to 0, does not necessarily mean that x and y are uncorrelated. Okay, there's an exceptional case to that, and that holds for Gaussian and Gaussian distribution. We shall not be discussing much about it in this course, but then except when mu x equal to 0 or mu y equal to 0. Okay, and one more thing about random, okay, independence will not be required much. If it's required later, I will let you know. Okay, okay, so you can in fact have a vector of random variables. Let's say x bar. I am denoting the vector with a underline below, okay, not the other one. There are various ways of representing. I am writing this one. So let's say it's x1, x2, all the way till xn. So it all of them are real numbers. Okay, I hope you what you understand by this representation. So it's a column vector containing real elements x1, x2, xn, and it forms an n cross 1 column matrix, and x1, x2, xn, all of them are themselves random variables. Now when you try to take expectation over this random vector x ex, what we do, since expectation, if you check properly, this expectation operator, it is actually a linear operator. Okay, so when I say linear, I mean I can go inside this matrix and apply expectation on each of them individually, and then I can write this as mu1 mu2 all the way till mu n. Okay, so I can denote it as mu bar, so mu1 mu2 mu n transpose. I need your notes. Yeah, so my notes, I'm after every lecture I publish my notes in the Google Drive link that is being shared in the NPTEL NPTEL course website. In the RTSP section, if you go there, you will find something called problem solving session. So when you go over there, you will be able to find course material. Over there you can find my notes. I hope you know how to access the notes, because these are also provided by NPTEL. Okay, so this is the expectation vector. Now once we have the expectation, we can also calculate something else as well. Let's say that. Okay, so what we call these a1 to n, these are actually jointly random variables. Okay, and they have some kind of a probability distribution p x1 x2. We had talked about 1 and 2 in that case, and we can generalize it to n random variables x1 x2 all the way till xn. Okay, now let us define another kind of a matrix, sorry, a column vector E, which is the difference between x vector and mu vector. Okay, so it's x1 x2 all the way till xn minus mu1 mu2 all the way till mu n, x1 minus mu1 x2 minus mu2 xn minus mu n. Achha, did anybody write anything? Oh, fine. It's xn minus mu n. Fine. Now I form a matrix expectation over E to E transpose. Okay, so what does E into E transpose mean? E is, okay, let me simplify further. It's E1 E2 En. Okay, so I give this notation. Ei is xi minus mu I. Okay, this is a random variable, this is a constant, because mean of a random variable is a constant, and hence this is also a random variable. So E I can write as E1 E2 En. So what is E? E is a n cross 1 vector. This is n cross 1 vector. Transpose will be how much? Can anybody tell me? What will be the dimension of this vector?
1 cross.
Good. So when it is 1 cross n, so what will be the product? So you have a m cross p and a p cross n matrix, so that will be, okay, m cross p cross n gives you m cross n. You cut out the p's. Okay, so similarly we have an n cross n matrix. So E into E transpose. How will it look? Let's see. E1, E2 all the way till En, and over here E1, E2 all the way till En. Now let me show you how this matrix will actually look like. Okay, let me try to show over here. So first multiply E1 with E1, you get E1 square. Then E1 with E2, E1. Let me write it as E1 2. I will tell you. I will clear the notation later. E1 then E3, E1 with E4, then E1 with E1. So I write E1n. So I am writing Eij as Ei into Ej. Okay. Now we move to the second row. E2 multiply with first column E1. So E21, then E2 with E2, so E2 square all the way till E2n. So Eij and Eji are the same. Okay, so we go over here and then En and with 1, so En1, En2, En square. Okay, so this matrix is a special matrix which is called the covariance matrix. Okay, so now what is the ijth element of this covariance matrix? It is Eij. And what was the Eij? Ei into Ej, and then it was, what was our, okay, so actually we take the expectation of this matrix, then it becomes a covariance matrix. Okay, we don't just do it, keep it as it is, because it's a random variable and I need a covariance. So covariance, if you saw earlier, so covariance was expectation of the x minus its mean into y minus its mean. Can you see the similar structure over here? Ei, Ej, and what are this Ei, Ej? X minus mu, xi minus mu I. Okay, so that's what I'm writing now. What is Ei? Xi minus mu I. So there should be an expectation. There should be an expectation sign, xi minus mu I, xj minus mu j. So is the covariance between the random variables xi and xj. And moreover, if you note, ci comma j is equal to cj comma I. So what does it mean? What kind of a matrix is this? What kind of a matrix is this? Anyone? Okay, so it's called a symmetric matrix, where the non-diagonal elements a21 equal to a12, a31 equal to a32, that kind of a property holds true. And if you see the diagonal elements ci comma I, what is that? Expectation of ei square, and if you look at it more closely, xi into mu I square, and that is nothing but sigma I square. So the diagonal elements of covariance matrix is variance of ith random variable. Okay, very important property. I guess your assignment has already been posted and it's due by 13th or something like that. So there is one question, so you maybe in exam also this question might be asked, so it will be helpful for you. So a special case, let's say the random variables x1, x2 all the way till xn, all of them are mutually uncorrelated. Note the word uncorrelated. And what did I say about the condition for being uncorrelated? The covariance must be 0. The covariance must be 0. And what was covariance? This quantity. And we have the covariance matrix over here. So what does that mean to be uncorrelated? So it means any random variable xi minus mean with another random variable in that set from 1 to n, that covariance is 0. It's provided that I is not equal to j. And what does this means? Ci ij is equal to 0 or I not equal to j. Okay. And so how will my covariance matrix look like? We know that variance cannot be 0. Okay, there is a separate proof for that. I'm not proving that, but then variance is actually if your variance is 0, it means your random variable is no more random. It is a deterministic, it is a random variable with value 0, and that 0 occurs with a probability 1. Okay, you may try that. You may try to check what does it mean to have sigma square equal to 0. Okay, provided the mean is 0. If mean is non-zero, then also check what does it mean. Okay, it has a special meaning. So the randomness goes away when your sigma square, as I told, this means variance. How far is your how likely is your random variable to be far away from the mean? So when it's not likely to be far away from the mean, that means your random variable always takes the value mu with probability 1. Is that clear what I am trying to explain over here? Why sigma square cannot be 0? Shabrish, Vamshi.
Can you repeat it again?
Okay, okay, good. So if you check sigma square equal to 0, what is the definition of sigma square? It is expectation of x minus mu whole square equal to 0. And if I break this further, x square minus mu square equal to 0. Oh, x square is mu square is equal to 0. And what does it mean? Minus infinity infinity. Or rather I can say like this, minus infinity to infinity x minus mu whole square fx dx equal to 0. Okay, so very important thing is this is always greater than equal to 0, and since this is square, this is also greater than equal to 0, right? Or am I wrong somewhere? Fx was greater than equal to 0. If you check my, yeah, the PDF is always greater than 0 and a real quantity, and since this is a square, so it is greater than equal to 0, and since I am assuming it's a random variable, this has to be, it cannot be completely 0. Okay, it has to be non-zero somewhere, otherwise you cannot have this integration of f of x dx equal to 1. Okay, it has to have some value somewhere. So what does it mean? In order to have this 0, it means that my x has to be equal to mu. Okay, only in that case, if I put x equal to my mu for all x, this becomes 0 and you get 0. Vamshi, is that clear?
Yes, thank you.
Okay, welcome. So the covariance matrix in this case, as I was so what was it mentioning, that actually the diagonal elements will never be 0 because they are the variances. Diagonal elements are variances and variances are non-zero. So sigma 1 square, sigma 2 square, diagonals are sigma n square, and the rest of them, since they are uncorrelated, all the values will be 0. All the values will be 0. So you also denote it sigma 1 square, sigma 2 square, sigma n square. Such a matrix is called a diagonal matrix. So whenever you see a diagonal matrix for some random vector, realize that all the random variables are mutually uncorrelated. Okay, so both all the random variables are mutually uncorrelated. So this was enough for the uh, basic probability division. Let me check if something else has to be covered. No, it doesn't seem so. So you can, there's another course going on in parallel in NPTEL, which is on adaptive signal processing, adaptive systems and signal processing. You can also go to that course. Okay, how can I contact? Oh, see, for my notes, I let just hold on a second. Let me share my contact number. Okay, let me contact. I am sharing my email address with over here. Ouharda dot ghosh@iitgn.ac.in. But in order to get notes, you have to access the Google Drive that is being provided by NPTEL. Okay, so let me start with the adaptive filtering, the actual content of the course. Okay, so what we shall study about is the Wiener or the optimal filter. Okay, so what does an optimal filter behave like? Okay, so let's say I have an input signal x of n. Now see, all our signals over here will be random in nature. Okay, unlike whatever we have done till week 6, all our signals were deterministic. We were able to, we gave some kind of a closed form equation, sinusoid, some delta function, some unit step, all kinds of functions they could be represented. We were able to determine what will be its value after some time, any instant of time, right? But now we are dealing with random signals, so their description will be a bit different. So this signal x of n actually passes through a filter whose FIR filter whose coefficients are W0, W1 all the way till Wn minus 1. ZD is an n-tap filter and the FI filter output is y of n, and as I mentioned earlier, there is a reference signal d of n with which the y of n is compared and you get e of n. What is our objective? Okay, now before stating our objective, we state what kind of signals are there. Xn is real, zero mean, and WSS. So what does WSS mean? WSS means white sense stationary and in very simple words, let me tell you what does it mean. It means mean is constant, means expectation of x of k is fixed, and since it's some constant mu, and in this case it's 0, it's mean, not memory, mean. And the correlation is dependent only on time lag. What does it mean? So let's say correlation x of k minus m. So this is a random variable at instant k. I mean, it can be the signal value at the kth index and a signal value at m instance before. Okay, so this correlation is actually a function of this distance only. Okay, it's not a function of the lag as well as k. Okay, In that case, I wouldn't say that it's stationary. It's stationary because it's independent of this k. And most of the real life applications, our signals are white and stationary. Similarly, our dn will also be real, zero mean, and white and stationary. Okay. Now, what is our aim? Our objective? Yeah. Okay, Aditya. So this is an official platform. So in case you have any doubts, please you can switch on the microphone and then write. Objective is to minimize error en or to ensure yn is the best copy or estimate of d of n. But then I shouldn't say minimize en directly, because if I try to minimize en directly, I can take it down to a very negative value, say minus 10 to the power 5. And when I say minus 10 to the power 5, that means yn and dn have no connection, they are very far apart. Okay, so it should be some kind of a positive value. So you may have some kind of a, okay, so for instance I can say let's minimize the variance, the variability of this en, because this is also a random variable, xn is also a random variable, it is passing through a filter, so yn is also a random variable, and automatically en is also a random variable, so it has some kind of a variance. Now my objective will be to minimize this variance. Okay, so now some notation, math coming in. This w vector, the weights of the filter coefficients of the FIR filter, I denote them by w0, w1, wn minus 1, and the input, and this representation, keep in mind this representation, vector of random variables. So what I am dealing with now is nothing but vector of random variables. So w bar is this. So now we have a time dependent vector x bar of n. What does it contain? The signal at time index n, 1 delay, 2 delay, 3 delay, all the way till the last one. Okay, so basically how does it actually look like? My filter that I mentioned, yeah, so the xn, xn minus 1, xn minus 2, here it was an L tab, so xn minus L plus 1, so all these values are being stored in some kind of a vector, column vector. So that was our notation for x bar of n. So now this signal y of n, you know, it's the dot product, is the convolution between w and x bar, or we can also write it as w transpose of x bar n is w0 xn, w1 xn minus 1, all the way till wn minus 1 x of n minus n plus 1. Okay, and also you can write it as x transpose of n w bar, because they are all real. Now we have some quantity is called the correlation between xn and dn. What was this dn? dn was the desired signal that I mentioned in the beginning. What is that? So it's again a column vector which is expectation of x, this vector with this dn. So it will have things like rxd of 0, rxd of 1, all the way till rxd of n minus 1 where rxd of m is expectation of d of n times x, sorry, x of n minus n. Okay, this is the correlation vector. And then we have the covariance matrix. No, okay, so previously we mentioned the covariance matrix as the expectation of x bar minus mu bar times x bar minus mu bar transpose. This was the covariance matrix. Similarly, we have the correlation matrix. This is the vector equivalent of the correlation matrix. Okay, so this P of n, you term it as cross correlation. Why cross? I taught this in the previous lecture. Cross because there are two random ends, cross x and d, so crossing with each other, and this is the correlation. So you actually call this auto correlation with self. Crossing with this, it's not a cross two of them, it's a single one with own self. So that's why it's auto correlation matrix. So now let us check something. So what do you want to minimize? We want to minimize the variance. Okay, so let us check if this is the variance at all or not. Why did I write this? So let's check the expectation of the y. That's expectation of w transpose x bar of n. Now w, these all of them are constants, these are not random variables. Okay, w0 to wn minus 1, these are some fixed constants that we want to find. We want to find actually w0 to wn minus 1. This filter, I call it as an optimal filter. The optimal filter will try to produce a y of n which is as close as possible to d of n, such that the energy of the error is minimum, energy or variance. So since this is constant, I take out w transpose bar and then keep this. But then I mentioned that xn is 0 mean. So since xn is 0 mean, so all the elements xn, xn minus 1, xn minus n plus 1, they are also 0 mean. So I can put in 0 over here, I get a 0. In case you have any doubts, you may interrupt me at any point of time. Okay, so this is 0 mean. Now okay, so this is the expectation mean. Now let us check the expectation of En. This should be simpler, dn minus yn. Dn is also 0 mean, that I told you earlier. In reality, most of the real life signals are all 0 mean by default. So yn is also 0 mean, so the expectation is 0, so automatically the variance of En, expectation of e square of n minus expectation of en whole square, so this boils down to 0. So our objective is to minimize expectation of e square of n subject to, with what do we need to find? We need to find these sort of coefficients. Okay, so let us now try to find the expression for this e square of n. My queries from my topics, hold on a second. Yeah, actually Aditya Raj, for your information, this is an NPTEL PMRF sponsored session on the course of real-time digital signal processing. So unfortunately we will be able to take only doubts related to the particular week's module only. So I may not be able to address your specific query in this session. You may contact me later. Yeah, sure. So expectation of e square of n, so that is, how can we write this? Since this is a real number, so real number transpose is itself, so of e of n into e transpose of n. I am writing this for certain reason. So e of n can be further broken down as d of n minus y of n again I can write this as dn of n y of n transpose expectation of. Okay, now let me drop the n's and work with them, otherwise they will be tedious. So this is d transpose y transpose of d transpose minus dy transpose minus y d transpose minus y transpose. Okay, so d and y are real numbers, so we told for real numbers that the transpose is the same. So expectation d square, and see these are same, I can write 2 d y transpose, and this is also expectation of y transpose. I'll keep it split plus. Now let me break them apart. Expectation of d square minus 2 expectation d y transpose plus expectation of y transpose. Now our yn was w transpose xn. Note that these two are vectors. Okay, now I will again drop the n's. Okay, this doesn't have any, so it becomes e of d square minus 2 e d w transpose x whole transpose, then expectation w transpose x whole transpose, expectation of d square 2e d x transpose w. What we have done over here, a b transpose is b transpose a transpose. We have used this property plus expectation of, we are using the same property over here, x transpose w. So expectation of d square can be considered as the signal energy. D I mentioned was a zero mean, so since it's zero mean, so it's same as this expectation d square will be same in the variance, and variance also gives an estimate of the energy of the signal. So we write, but this is a random variable, so I write it as sigma d square. Now what can we do over here? W is constant, d and x are random variables, so I keep d and x inside and put out w. Now I do the same over here, I put w outside, I keep x over here, I can remove w from here. Let's go back and see some of the notations. Okay, so this one was p bar equal to, we can write x bar into d, and then this r we could have written as, so it will be expectation actually, expectation. Okay, so we have already written it in this symbol, x into x transpose. So that was our p was x into d, so this d is a scalar, so we can write this as p transpose w plus w transpose r w. Okay, so now what you can see, our expectation of E square is actually in this form of 2p transpose w transpose. So if you look at it very carefully, this is a first order in w, and there are two terms over here, so if you try to multiply and then check them, then you will get second order w0 square, w1 square, w0, w1, w1, w0, those kind of cross terms, so it's second order in wr. So what can we say? It is a quadratic in w bar. And since it's a quadratic, so what is good about it? So you know that quadratic functions have maximas or minimas. So based on our purpose, we are trying to minimize e square of n. So we are hopeful that we will be able to get some kind of a good minima. We will get some minima value. So actually look at it once again. We are actually dealing with multiple variables w0, w1 all the way till wn minus 1. So what we actually need to do, we need to take okay, so let me give this a symbol epsilon square. Okay, so to minimize, what do we need to do? We need to set the derivative of the function to 0. That's the first step. So del e square upon del w0, and we have to check it, do it with respect to all the variables involved. With respect to w0 will be 0, with respect to w1 should also be 0, with respect to wn minus 1 should be a 0, and in a concise vector notation I can write gradient with respect to w square should be 0. What does that mean? Del epsilon square del w0, del epsilon square del w1, del epsilon square del wn minus 1. Each of them should be equal to 0. Now without proof I am solving this. Okay, gradient epsilon square gradient, what was the value? Sigma d square minus 2 p transpose w plus w transpose r w. Sigma d square is a constant, so it remains as it is, minus 2 p transpose w. If you try to differentiate it, so it's like del x of a into x. A is a constant, so you take that a out and you will have w. The w will go out and I'll have minus 2p. Okay, you may try this out at home, or in case you want the detailed calculation, you may watch the NPTEL series on adaptive systems and signal processing by Professor Mrityunjay Chakraborty of IIT Kharagpur. There's an old course in NPTEL and also a new course, 8-week course, that is running live in this session, August session. Minus 2p transpose, and then if you check the second part also, you will have 2rw. Now so when del w epsilon square has to be equal to 0, what does it mean? 2rw. Now let me see that it's opt, minus 2p equal to 0, so w opt r opt equals to p. This w optimal is r inverse p. Okay, w opt, I am writing it once again, is r inverse of p. This is the optimal or Wiener filter. This is the best possible filter that you can get, which will minimize your error variance. Okay, this is the best, this is the theoretical boundary, this is the theoretically best possible filter that you can ever get based on xn, dn and the conditions that have been provided. Okay, is it clear for all? Shabrish, Bamshi, any doubt in any of the steps that I have done? Can you please confirm? Shabrish, Bamshi, are you there?
Yes, sir.
Okay, so any step, all the steps are clear? So but then there is one thing, this all of this has been done assuming that we had some fixed R and fixed P. This was one of our assumptions. We had some signal statistics, but then signal might keep changing statistics. So what do we need to do? If it keeps changing the statistics, we need to keep calculating R inverse. We also need to keep calculating P, and then we also need to multiply the two. And if you have ever seen the computational complexity, think about it, you have to compute the inverse of a matrix, and if you have, let's say, if you take, let's say, 10 samples, okay, you have to compute a 10 cross 10 matrix R, then compute the inverse of a 10 cross 10 matrix, and then again multiply. Intense computation involved, okay. So you can very well realize that you can never compute this R inverse P, okay. So this is a theoretical bound, or a theoretical best possible limit to that you can get, but in reality you cannot get it. So actually, first of all, since it is fixed, we need to go for an adaptive method, and for the adaptive method or adaptive filter, we use the concept of gradient descent. Okay, I'm taking a short break. You can come in for a while. Okay, so am I audible now? Please confirm.
Yes, sir. Audible.
Okay, thanks. So we use the concept of gradient descent. Now this concept of gradient descent you will also be learning in machine learning, deep learning, and all such courses. So basically the roots all stem from the same from the fundamentals of adaptive filtering, adaptive signal processing. So in gradient descent, what do we do? So what we wanted to find, we wanted to find w0, w1, their optimal values, okay. Should be n minus 1, okay. So what was happening over here is that we were calculating the expectation, and all of a sudden we landed upon a single value. So rather than doing that, what we do, that let's suppose I have some wi of n plus 1. Okay, so I do it, it is an iterative process. Okay, so let's say currently have some value of y of w of I. Now with that, from that I subtract a particular quantity, that, okay, del epsilon square upon del wi. Okay, so what is actually happening over here is that we want to minimize epsilon square. Okay, let me actually draw epsilon square with, let's suppose, w of I. So as I mentioned, this is a quadratic, it is quadratic in nature, and for example I take with respect to a single variable, it will have some kind of a parabola. Okay, and this is the minus wi opt. Let's suppose at the ith index, nth time index, I have this value wi of n. Now if I check the slope at this point, okay, if I check the slope at this point, the slope is del e square by del wi at wi of n. Okay, and the slope is positive. Now this, let's suppose the slope I multiply by some number mu by 2 times slope, and what do I do? I'll talk about this importance of this number mu by 2 later. I subtract this from wi. So what will happen? Will the next point go left or right? Can you please tell me? I have this slope which is positive, I multiply that with a positive number mu by 2. Okay, let me mention this, mu is greater than 0, and I subtract it from wi of n, this value. So where will my wi of n plus 1 be? Will it be towards the left or will it be towards the right? Shabrish, can you please tell me? You are subtracting a positive number from here, so it should be left, right?
Yeah.
Correct. So we will end up jumping towards the left side. So aren't we getting closer to wi of opt? Here the slope is a bit small, so the number that I will be subtracting will also be a bit small, and slowly I'll come to this region based on the value of mu. If mu is very small, what will happen? This is my w opt. Let's suppose I start from here. See, I take very tiny steps. Okay, small. So I am taking a lot of time to come over here. Okay, so I am being very slow in moving towards the optimal value. On the other hand, if my mu is very large, something very disastrous can happen. Rather than moving over here, I may end up moving over here, and then I may end up moving here, okay, I may keep on oscillating and diverge. Okay, so if mu is very large, it can diverge. If mu is very small, very slow, it will converge for sure, but it will slow. By converge I mean your w will reach the optimal value. So this we do for all the possible values of wi, and we write it as w n plus 1 in vector form is wn minus mu by 2 grad w of epsilon square. this mu is called the update parameter, and this is called the gradient descent based weight update. Okay, this is the weight update equation. Now if we try to write this gradient of epsilon square, we found it earlier. Okay, this value 2rw minus 2p, 2rw minus p. So let me write this, explain this further. Wn minus mu by 2. This mu by 2 was given intentionally so that I can cancel this 2. So what I get over here, Wn minus mu rw minus p, Wn minus plus mu p minus rw, and what was our p? P was okay, so p was expectation of x bar d, and what was r? R was expectation of x transpose, okay, w. So here is something that interesting that we do over here. So we do a very wild approximation. What is the wild approximation that we do? So this expectation of any quantity, let's say x bar, we can write it as x of n minus 1 all the way till x of n minus n plus 1 divided by n, limit n tends to infinity. Okay, this is the ideal value of this average, and in reality what we do, we take n equal to 1, we take one single value and replace it by a wild estimate. So when I have n equal to 1, we have this single xn. Is this clear what I have done? I substitute this average expectation of, okay, so it should rather be expectation of x. Expectation of x of n should be x of n, and similarly expectation x bar d, I write it as xn into d of n. Expectation, so all the averages are being converted into single values, x of n into x of n. X bar transpose. So if it was x bar, then it will be all of these vectors. So we are doing a vector average actually. So our w bar of n plus 1 becomes w bar of n plus mu of xn dn minus, which was rw, right, xn x transpose of wn, and that we remember what was it, it was y of n. So w of n mu bar of n dn bar of n y of n, this was y of n. Let me take out x bar of n dn minus y of n. What was dn minus y of n? It was our error. So what do we get over here? Okay, so this wn plus 1 is wn plus mu x vector n en. This is what I call the LMS algorithm, or the least mean square algorithm. Okay, so what we actually do over here is each of the weights are varied as per the equations that I am writing. All the weight coefficients are adapted parallelly. Is this clear, whatever I am writing? Shabrish, are you there?
Yes, sir.
So it's clear, right?
Yes, sir. What if xn and d of n
Huh?
are dependent?
What? Xn?
Xn and dn are dependent, then we can't take that wild approximation.
Xn dn are dependent. Which approximation are you talking about?
Wild approximation.
I am taking Xn and dn are not dependent on each other. Xn and dn are not dependent on each other. Even if they are dependent, I do an approximation. Means it's you are correct that I don't know whether wait, let me mute you once. It's also not lot of noise. See, that's why I'm calling it wild. Okay, because although I'm not supposed to, but I do take it, and because of this approximation there is some kind of a noise injected in your system. Okay, so because of this noise, what happens is that because of this approximation, let's say I have a weight, I want to calculate what is happening with W0 after every iteration, and this is supposed to be the optimal value. Okay, so what I see is that initially in the beginning I am over here oscillating slowly. I finally reach the optimal value, but then you see it's not flat. I keep oscillating around the optimal value, so I am converging in a expected or a mean sense, but I'm not converging absolutely. I am having some kind of an oscillation, some kind of variance, and because this is due to the approximation error. Okay.
Yes, sir.
Okay, so we have finally completed the LMS algorithm, so that marks the end of today's lecture. Okay then, good
So
night.
how the
Yeah.
algorithm,
How the
LMS algorithm
how
will
the
give
algorithm is? You're having a lot of noise. Can you please write it down? Yeah, you can tell now if you want. Shabrish, are you there? Oh, how LMS algorithm helps to detect the desired frequency. Um, okay, so there is a separate paper on that. Okay, so I will not, unfortunately, due to the scope of this lecture or this tutorial, I will not be able to explain that in detail, because that will again take another 1 hour, half an hour. But then I can, if possible, I can share the paper in the next tutorial, next session. So would that be fine? Because that's again another sort of a big derivation, so it's complete math involved. Okay, Okay then, thank you everyone for attending this session. Have a good day. Good night.